Now we come to the Lebesgue number lemma and the uniform continuity theorem. So the Lebesgue number lemma, the idea behind the Lebesgue number lemma, is to have, whenever you have a space X, so let's say you have a space X and you have some open cover of this space X. Okay, so all these red circles are open sets, say AI, A1, A2, A3 and so on. Now if it is, so for example, let's take a point, one of the points in this space X, and let us take a ball of some radius, say R. This is a metric ball, BDXR, and we see that this ball does not lie entirely inside any of the open sets that we have in the open cover. However, if you shrink this ball, if you make it smaller, then this a new ball, say with the radius R prime, this lies within this set, within this open set, and within this open set as well. So this is the idea of the Lebesgue number lemma, is to find a small enough radius delta, with radius delta, such that the metric ball with any center X and radius delta lies in some AI for some I. Okay, so given any open cover, if we can find such a number delta, then we call this number to be a Lebesgue number for this open cover. And so we make the following definition. So definition of the Lebesgue number of an open cover. So for this we take a metric space, XD is a metric space, and let A be an open cover of X. If there exists a delta such that the boundary, this says that for any chosen point X in X, the metric ball of with center X and a radius delta lies within some A from this collection of open sets which form the open cover. So for some A belong to this open cover. So such a number, any such delta is called a Lebesgue number. Lebesgue number for this open cover A. And let us make another definition. So this is a metric space with the Lebesgue number property. And this says that a metric space XD is said to have the Lebesgue number property if any open cover of X has a Lebesgue number. So if you choose any open cover of X, then there exists a delta such that the metric ball of radius delta for any chosen point within X lies in it is entirely contained in at least one of the open sets in the open cover. So in this case, this metric space is said to have the Lebesgue number property. This is the Lebesgue number property, and the theorem, which is usually called the Lebesgue number lemma, but I am writing it here as a theorem, Lebesgue number lemma. It states that a compact metric space XD has the Lebesgue number property. Meaning that given any open cover of this space X, you can always find a delta such that even if you choose any arbitrary point and take the metric ball of radius delta, then it will lie completely inside one of the open sets in the open cover. So let us prove this theorem, and we will use the extreme value theorem that we have proved before to show this result. So proof. So let us take an open cover A, an open cover of X, and since X is compact, we can find a finite subcover. Let us call this A1, A2, AN is a finite sub collection of this open cover A, and this covers X. Now define the complements of each of these sets. These are closed sets Ci, and for using these Ci's, we can define a function and a function f from X to the positive real line, and this function is defined as the average 1 over n. So there are n sets in our subcover, so you take 1 over n and then take the sum I equal to 1 to n of the distances from this chosen point X to each of these sets Ci. So we have already shown that since the function dxa is continuous for fixed A, then f is a finite sum of continuous functions. So let me write it here. So f is a finite sum of continuous functions, and so it is continuous. And now we can use the extreme value theorem, to deduce that f achieves its minimum value. So in particular, there exists a delta belonging to the set 0 plus infinity, such that delta is less than or equal to fx for all x in x, and this delta in fact is of the form f of x naught for some x naught. And I claim that delta is positive. So let us see why delta is positive. It should suffice to show, so it suffices to show that f of x is positive, strictly positive for all x in x, and because f of delta is of the form f of x naught, so this is greater than 0. So then we will have that delta is greater than 0. So why is f of x greater than 0? So for any x in x, we can choose I in the set 1 to up to n such that x belongs to ai. So the subcover that we chose of the sets ai, so x belongs to one of these sets, so there exists an I such that x belongs to ai. Now since ai is open, there exists an epsilon greater than 0 such that the metric ball with center x and radius epsilon lies inside ai, because this is just the metric, the basis for the metric topology. And now this means that the distance between x and ci, which was the complement of ai, this is greater than or equal to epsilon, and so we have that f of x, which is equal to 1 over n sum dx ck k from 1 to n. This is greater than or equal to epsilon over n. So this is strictly positive. So we have shown that we can always choose a strictly positive constant for fx, such that fx is greater than or equal to that strictly positive constant, and therefore fx is strictly positive for all x. And this implies that the minimum value delta is greater than 0. And now what we are claiming is that delta is a Lebesgue number for this collection A. So we have to show that given, so for any x in x, the metric ball with radius delta lies inside one of the sets ai for let me write ak for some k in 1 to up to n. So why is this true? So to show this, note that we have that delta is less than or equal to f of x, and this is less than or equal to d of x cm, where d of x cm is the largest of the values dxci for I in 1 to up to n. So this is because we have f of x, which is just 1 over n d of x ci I from 1 to n summation, and if you take the maximum of all these numbers, so this is less than or equal to 1 over n I equal to 1 to n d of x cm. So each of these is less than or equal to dxcm, so you can just replace each of them with each of the ci's with cm, and we have this inequality. But this is nothing but d of x cm. So we had this lower bound delta already, and now we have an upper bound which is given by the the distance between x and cm. So for some m we have this inequality, but this implies that the metric ball BD with center x and radius delta lies completely inside AM. So you have this point x, and you have this closed set CM, and we are claiming that this distance is greater than delta. This is some r which is greater than or equal to delta. However, if you take any metric ball BDX delta, then this doesn't touch CM and therefore lies completely in the complement of CM, which is nothing but AM. So AM is CM complement, and therefore we have shown that this delta is our required Lebesgue number. So this proves the Lebesgue number lemma. Now, as a corollary of the Lebesgue number lemma, we can reformulate it in not in terms of metric balls, but sets with given upper bound for the diameter. So it says that given any open cover A, there exists a delta such that any subset B of x which has diameter less than delta lies completely inside some open set from this open cover. And this is simply because so let delta be, so here again x is assumed compact, so this is compact. So let delta be the Lebesgue number of A, and then the set B. So choosing any point x within B, the set B lies completely inside the metric ball with center x and radius delta, and this is inside some A for some A in A. So this proof is rather simple, and we can deduce it easily from the previous Lebesgue number lemma that we have just shown. So this Lebesgue number lemma in both these forms is a very useful tool, as we shall see, and is probably one of the most useful when it comes to compactness in metric spaces. And now we are ready to prove the uniform continuity theorem. So to generalize the idea of uniformly continuous functions from defined on real numbers to real numbers, we will give a definition of uniformly continuous functions between two metric spaces. So a function f from two metric spaces x, y and y, x dx and y dy, is called uniformly continuous if given epsilon greater than 0, there exists a delta greater than 0 such that dx of x, y, or maybe I should write x1, x2, x1, x2 less than a delta implies dy fx1, fx2 is less than epsilon for all pairs x1, x2 in X. So this delta, the only difference between the definition of continuity and uniform continuity, difference between the definitions of continuous and uniformly continuous functions is that the number delta greater than 0 may depend on a specific point, x. So meaning that different points might have different deltas. You cannot choose a delta which is independent of the chosen point x for continuous functions. So in general, for continuous functions, the delta will depend on the choice of the point x. So in the epsilon delta definition, we choose an epsilon greater than 0 and a point x, and then we conclude that there exists a delta. But for uniformly continuous functions, delta is chosen independently of these points in x. So this is the difference between continuous and uniformly continuous functions. And the uniform continuity theorem, now the uniform continuity theorem can be stated. Uniform continuity theorem. So the uniform continuity theorem states that if f is a continuous function between metric spaces, is continuous, and x is compact, then f is uniformly continuous. So of course, a uniformly continuous function is continuous, but the converse is not true, and this theorem gives us a sufficient condition, a criteria when a continuous function is uniformly continuous, and this is precisely when the domain is compact. So let us see a proof of this theorem. So to prove this, take an open cover of a y with sets of the form b dy y, and with some epsilon by 2 radius. So we choose epsilon greater than 0, and we take an open cover of y with sets of the form metric balls of radius epsilon by 2, and with centers y. And so this is an open cover. So y is actually a union of all these open sets indexed over y. And now, so let me call these sets u, y, epsilon. These are the sets, and then the sets f inverse of u, y, epsilon are open in X and form an open cover of X. So because u, y, epsilon, these sets cover y, therefore the inverse images will cover X. And now we can use the Lebesgue number lemma. Now choose delta such that for any x in X, the metric ball for X with radius delta and center X lies inside some the preimage of some uy epsilon. So let me call this uy naught for some y naught in y. So each of these metric balls with radius delta lie inside one of these, and this is precisely the definition for uniform continuity. So this means that given any 2 points x1 x2 in x such that x2 belongs to BD x1 delta, then this means that BD x1 delta which contains x2 inside some inverse image of some y naught for some y naught in y, and however this means that the distance in y between fx1 and fx2 is less than or equal to the diameter of this set uy naught epsilon, and the diameter is precisely epsilon. So this means that we have chosen a delta which is independent of any given point, such that whenever x1 and x2 lie within distance delta of each other, the images fx1 and fx2 lie within epsilon. So this proves that our function is f is uniformly continuous, and this completes the proof of the uniform continuity theorem.